Please welcome everybody, the jury members and also the general public to this public presentation of the PhD thesis of Fernando Miró Miró. So some weeks ago we had the private defense and the jury members have already been able to view and ask questions to the candidate and view the thesis. Today we will see the final public presentation and then there will be time for questions again. So please, if the supervisor agrees, the supervisor is Gérard Degrez, the thesis promoter, then we can start with the public presentation.
It's fine with me.
Okay.
Yeah, so hello and welcome everyone to this atypical PhD defense, where I will introduce you to the work I've been carrying out these past almost 5 years at the Karman Institute, based on, well, focusing on hypersonic boundary layer stability and transition in the presence of ablation phenomena. The thesis is already available online, so if any of the users want to take a look through the things that I'm saying, it's in my ResearchGate account, so you can just download it directly. Okay, so let's get to it. So first of all, why is it that we are interested in investigating transition?
Voila. So maybe you have to repeat.
Okay, yeah. I'll just start over then. So back to the beginning. So why is it that we are interested in laminar to turbulent transition? Well, the reason is that pretty much any form of air transport is in one way or another affected by it. In hypersonic cruise and atmospheric entry vehicles, we are mostly concerned of how transition affects the surface heat flux that the thermal protection system might withstand. Whereas in conventional aviation, what we are mostly concerned of is on its impact on the aerodynamic drag. So what is laminar to turbulent transition? So to explain this, I like to use the example that my friend Kuhn often uses, and which almost everybody can relate to. So if we think of when we open our water faucet at home, if we open it just a little bit, we will see a thread of water that is very ordered and it looks kind of clean. So this is what we call a laminar flow. If we then open our faucet a lot more, we will see that the flow is no longer ordered and clean. It becomes this chaotic mess that it varies a lot with time and so on. So this is what we call a turbulent regime. This phenomenon that we can observe in our everyday life is the same that actually happens in more complex systems, such as an atmospheric entry vehicle. What we have is that close to the tip of the vehicle, we have a laminar flow, and after a certain extent, it becomes turbulent. The same happens on an airplane wing. So close to the tip, we have that the flow is laminar, and after covering a certain distance over it, it eventually becomes turbulent. So what we're interested in is in being able to predict where this transition from laminar to turbulent occurs. And because having either one or the other regime is going to strongly affect the heat flux in the hypersonic case, or, as we said, the aerodynamic drag in the conventional aircraft case. So at the end of the day, what we want to know is where the flow becomes turbulent, and then either design or size our thermal protection system accordingly, or come up with some smart engineering solution so that we can get rid of the problem altogether. Okay, so how does the flow become turbulent? So if we imagine a flat plate over which our boundary layer is gradually developing, we have that, as we said, at the beginning, the flow is laminar. And after a certain distance, a series of perturbations enter into the boundary layer. These perturbations first grow linearly and with independence of one another. But after a certain extent, they start interacting with each other in a 3D fashion and ultimately lead to a vortex breakdown, turbulent spots, and finally a fully turbulent flow. So this is what we call the natural transition path, and it corresponds to a low disturbance environment. However, if we have a higher disturbance environment, so let's say this could be a stronger, like a rougher surface or a higher level of turbulence in our free stream, then we can have stages where there is a transient growth or even a series of bypass mechanisms. So if for example, we have a strong protuberance, like a very big roughness element on our surface, it is possible that this just completely bypasses the entire process and the flow just becomes immediately turbulent behind it. On top of that, if we have high temperature flows, like the ones that are featured in atmospheric return missions, there are a series of additional considerations that we have to take care of. So if we are at a lower temperature, we have that our gas can store energy either in a translational mode, which means just basically the molecules moving around, or in a rotational mode, which is the molecule rotating about its axis. However, as temperature increases, the molecule also starts to vibrate with each other. This is what is called vibrational excitation. And if the temperature is high enough, this excitation will eventually lead up to a dissociation of the molecule. So the two atoms separate from one another. If we continue increasing the temperature, eventually we're going to reach a point where the electron levels are excited. So the electrons surrounding the atom are in an excited state. And if the temperature is high enough, this will lead to the electron just leaving the atom and having a partially ionized plasma. On top of that, so very often in atmospheric return missions, we design our thermal protection system such that it ablates and fails. It pyrolyzes and ablates in order to alleviate the high heat fluxes that it's withstanding. Yeah, so in that case, we have, as we said, a recession of the thermal protection system. So basically, we let the thermal protection burn in order to alleviate the heat fluxes that we would be receiving. And this is what we call ablation and pyrolysis. These are not fantasy scenarios. And actually, if we look at typical atmospheric return missions, such as the Space Shuttle or the Apollo mission, we see that they'll go well within the ranges where all these phenomena have to be taken into account. So basically, there are a series of factors affecting transition, which are the Reynolds number, the Mach number, surface geometry, the inflow turbulence and noise, pressure gradients, the level of surface roughness, cooling or heating of our boundary layer, or suction or blowing through the surface. And it is particularly interesting to see how ablation affects transition, because within it, we have three of these main factors. There is a modification of the surface roughness due to the irregular burning of the thermal protection system. There is a cooling due to the series of chemical reactions that occur. And there is a blowing of pyrolysis gases into the boundary layer. So within this frame, the objective of this doctoral research was the development of a simplified model for the influence ablation has on boundary layer transition, permitting for a phenomenon decoupling. All right, so having introduced already the motivation and the objective, I will now talk about the methodology that we've been following to tackle these problems, the different tools that we've used and or developed for it, and finally present the most interesting results that we've obtained and close it up with a small summary. Okay, so starting with the methodology, there's a wide variety of techniques that we can use to study laminar to turbulent transition, and we can kind of arrange them in order of increasing fidelity and, of course, computational cost. So at the top, we would have DNS, direct numerical simulation, which offers a full description of the flow equations, but that are, of course, very costly. Somewhere down the line, we have LES, so large eddy simulations, followed by stability methods, correlation-based, RANS-like approaches, and experimental correlations. And, well, kind of out of this computational classification, we've got experiments, which, of course, offer a full description of the problem physics, but have a bunch of other problems associated with them, like effectively reproducing the flight conditions in your facility, for example. So the first three of these techniques are mostly restricted to theoretical studies, so like fundamental research due to their high computational cost, whereas the last two are only used in vehicle design because they are not very accurate, basically. And somewhere between these two worlds is our stability methods, which is the technique that we use. So the basic idea behind a stability method is to start off from a high quality laminar base flow. So basically our faucet when we weren't turning the tap too much, and introduce into it a series of perturbations. If these perturbations grow, we say that the flow is stable. Whereas if they are damped out, we say that the flow is stable. But if they grow, it is unstable. And it will be the growth of these instabilities that eventually leads to turbulence. So we can think of our boundary layer like a simplified physical model. So like just a surface rolling on top of a surface. Just a ball, a sphere rolling on top of a surface. And a stable boundary layer would be like a concave surface, where if we displace our state from equilibrium, it will just oscillate and eventually go back to its original state. Whereas the unstable system is where a small displacement actually moves it away from equilibrium. In reality, boundary layers are not either completely or completely stable or unstable. What we usually have is something like this. So where the system is stable to certain perturbations, but not to others. And where this typically depends on the wave conditions. So either the frequency or the span-wise wave number, or basically the characteristics of these perturbations. OK, so the next question is, how do we model these perturbation terms? Well, for that, we have a variety of different stability theories. And we will choose one or another depending on the specific problem at hand. So depending on what shape our perturbations have in the wall normal in the spanwise direction, and also how much of the transition range we want to account for in our model. My work was focused on linear stability theory, which is one of the most simple of these theories. But as we will see later, it was done in such a way that it can be relatively easily extended to more elaborate stability theories. OK, so what does LST consist in? Well, the first thing we do is we decompose, as we said, our flow variables into a mean component plus a perturbation. We then linearize the equations by dropping higher order perturbation terms. We make a modal decomposition where we effectively assume that the perturbation is periodic in the spanwise and streamwise direction and in time. And we assume the flow to be locally parallel. With all this, we managed to boil down our Navier-Stokes equations to a generalized eigenvalue problem, which we can solve either to obtain the perturbation wave number for a fixed perturbation frequency. This is what we call the spatial problem, or the perturbation frequency for a fixed perturbation wave number. So that's what we call the temporal problem. All of my analyses are focused on the stability, on the spatial problem. So we fix a real value for the perturbation frequency and the spanwise wave number, and then obtain as a solution of this eigenvalue problem a complex number of which the minus imaginary part corresponds to the growth rate of the perturbations, so how much they grow in space, and the real part corresponds to the streamwise wave number. So what is their oscillating content in the streamwise direction? OK, so this same methodology we deploy on the flow equations, which can vary slightly depending on the flow assumption that we use. And of course, these will require appropriate boundary conditions. I won't enter into details with this, but there's 3 chapters of the thesis dedicated to it. So there's chapter 2, 5, and 6, which work on basically detail all of these equations. So if you're interested, we can also discuss it in the Q&A. An important thing to know is that linear stability theory directly models the first stages of perturbation growth, so the stages of eigenmode growth. And to actually predict where transition will occur, we have to use the so-called semi-empirical e to the n method, which basically draws a black box over the remaining stages of perturbation growth. And we correlate the location where transition is expected to occur experimentally to the amplitude that perturbations would have at that station if they were to continue growing linearly. So the actual methodology that we follow is we start off from the perturbation growth rate. So this is what we plotted here. It's at what rate the perturbations grow for different frequencies. So that's the different colors as a function of the streamwise position. We then integrate these growth rates, and in that way we obtain the amplitude of each of these perturbations of each of these frequencies at each location. And by taking the envelope of all these curves, we have the amplitude that the most amplified perturbation has at all positions. And then knowing at what amplitude one would expect transition, we can estimate what the transition location is. So it might seem surprising that with a theory that, looking at the sketch at least, is only focused on this very short range of the whole process, we are capable of getting some meaningful predictions. But in reality, what is happening is closer to this. So the size of the linear growth region is actually much higher, which is why we can get away with all these simplifications. Regarding the actual physical mechanisms that we are investigating, this dissertation was focused on second mode instabilities, which are known to be dominant in high-speed flows in the absence of crossflow. They are high-frequency acoustic instability waves, which are confined below the relative sonic line. This is a rather mathematical explanation, but there is a more physical one that was proposed by Dr. Kuhl recently, which consists in interpreting that the instabilities are actually confined under the thermoacoustic impedance that is associated to the density gradient. Second mode waves are two-dimensional, which means that they have a zero spanwise wave number, and if the wave speed is low enough, so just to have another region of relative supersonic flow on the top, they are what we call the supersonic modes, which are slightly different because they radiate energy into the free stream instead of rapidly decaying exponentially. All right, so now how are we going to do all this? Well, as we said at the beginning, there's two parts to this analysis, right? There's first solving the laminar baseflow problem, and then the propagation of instabilities of perturbations within that baseflow. So regarding the laminar baseflow problem, we've used one of two different tools for it. The first is a CFD++, which is a commercial solver solving the Navier-Stokes equations with a second order finite volume method and with an HLLC approximate Riemann solver. The second is the decaf flow solver, which we developed together with the Texas A&M group and with Kummerut from TU Delft. It's open source. And it solves the quasi-3D boundary layer equations with spectral accuracy in the wall normal direction. I won't enter into the details of this solver because we could spend forever just talking about it. Chapter 7 of the thesis is entirely dedicated to it. But the bottom line is that it's quite powerful and it has a lot of modeling capabilities. So if anyone from the audience is interested in using it, we're about to release this open source. So just shoot us a message. We already know that the NASA Langley team is interested in using it. So yeah, just shoot us an email, basically. All right, so that concerns the laminar baseflow problem. Now let's look at the stability one. As we said, we're performing LST analyses, and for that we use the VESTA toolkit, which was initially developed by Fabio Pinna during his PhD. And well, which it has been extensively remodeled to account for all these physical phenomena that we want to put into it. So as any LST solver, really, it receives the laminar baseflow field together with a series of flow parameters and stability parameters. It maps everything onto the computational grid. It builds the system matrices and then effectively solves the eigenvalue problem, obtaining, as we said, this complex wave number. The most interesting of these blocks, and where all the actual physical modeling goes, is in the building of the system matrices. And one of the most interesting things of VESTA is that we can do this through an automatic derivation and implementation tool, which effectively starts from the Navier-Stokes equations in invariant form, and then applies all the hypotheses that are necessary in order to derive the stability equations. These equations are then implemented into actual scripts, which can be run by the rest of the tool. Again, I won't enter into much details about this automatic derivation implementation tool, but chapter 8 of the thesis is entirely dedicated to it. So there's a lot of information there. the most interesting thing of it is that by slightly modifying the hypothesis that it imposes, we can obtain also build scripts for other more fancy and elaborate stability theories. So this is what we've been doing together with Ludovico Zanus and with Ivan Padilla. So we've been applying it to linear PSE or to nonlinear PSE and spanwise biglobal. There's a small note that must be made regarding this automatic derivation and implementation, and it concerns the division between independent and dependent quantities. So, for example, in CPG, in perfect gas conditions, we have that the independent quantities are the three velocity components and two thermodynamic variables, so like pressure and temperature. And the dependent would be pretty much anything else. So viscosity, thermoconductivity, entropy, or density. In our stability equations, we actually have the perturbation quantities of all of these. But at the end of the day, we only solve for the independent perturbation quantities, which means that we have to find a way to express the dependent perturbations as a function of the independent. And to that, what we do is we exploit their functional relationship to them, which conveniently in perfect gas are rather simple expressions. So we can just Taylor expand this around the base flow and basically substitute them. So once we do this, we get these thermodynamic derivatives, which, as we said, for perfect gas can be computed relatively easily because the expressions are not very complex. But the thing changes when we move to more complex physics. So we look at a high enthalpy scenario, we have a lot more dependent quantities, and their dependency on the independent is a lot more complex. So these expressions are no longer straightforward, and obtaining, as we said, these thermodynamic derivatives can be pretty error prone, which is why I developed a specific module of this automatic derivation and implementation tool, which starts off from the actual expressions for all these properties. It then differentiates them analytically and then implements all this into a series of scripts and functions that can be used by the rest of the code. Okay, so that's why we're doing it, how we're doing it. Now let's look at what we've actually done. So looking at the results, as we said, in ablation transition problems, we are concerned of how ablation affects three of these key factors, which are the surface roughness, the chemistry that occurs, and the blowing of pyrolysis gases. First of all, regarding roughness, it's a very active field of research in and of itself. Just looking at how roughness affects transition. And on top of that, we're still not very sure how ablation, so what sort of roughness patterns you can expect from ablation. Actually, there was an experimental investigation working on that at the Institute, and we provided like some theoretical support. But it was still at a very early stage. So yeah, it was still a very preliminary study. Together with Ivan Padilla, we also looked at coupled roughness chemistry effects, but looking at an isolated roughness element, so like a protuberance on the surface, which is not really representative of what you would encounter in ablation scenarios. Which is why my dissertation kind of leaves roughness at a side and focuses on these two other phenomena. So on the blowing of mass through the surface and on the chemical reactions that occur within the flow. So we first look at them decoupled and then together in an ablation-induced case. So first of all, let's look at the blowing effects. So there were three main lines of research that we followed, which also coincide with the three subsections of Chapter 9. The first was a numerical experimental investigation of a Mach 6 flow on a 7-degree cone with surface blowing, which we published last year at the AAA journal. The second was an investigation on how the injection gas composition modifies the transition dynamics, and this just got recently published at the Journal of Fluid Mechanics. And finally, the third was a study on the sensitivity of the stability characteristics to the surface boundary treatment, which, well, a preliminary version of this we presented at OCAS already 3 years ago, and the actual full work was later published in Physics of Fluids. So I'm going to leave this third one out of today's presentation because it requires a bit of a more thorough theoretical background, and I'm going to focus on the two first. So first of all, the numerical experimental investigation. What we did was to provide theoretical support to a series of experiments that were conducted at the VTI H3 wind tunnel, and where they basically got a 7-degree half-angle cone and put it in a Mach 6 flow, blowing air through a porous section in the middle of it. This porous section was actually a perforated aluminium with yet another porous layer under it, much finer, and which allows us to be sure that none of the waves in the blowing chamber actually reaches our boundary layer. And conveniently enough for us, it also theoretically allows us to apply a boundary condition that was actually developed for porous walls for passive porous walls on this blowing case. So this is one of the things that we wanted to determine. So can we use this passive boundary condition on a blowing case? Okay, so we went ahead and did just that. So what we're seeing here is the transition Reynolds number. So a measure of how at what streamwise station transition onset occurs as a function of the blowing parameter. So basically how much mass we are injecting through the flow. And the first thing we see is that, as we would expect, the more mass that we inject, the lower is the transition Reynolds number, which means that blowing effectively advances the transition front. So transition occurs sooner if we blow, and even sooner the more we blow, basically. So that's very good. So then we said, okay, can we reproduce this with our tools? And by using the homogeneous boundary condition, so just forgetting about the porous surface, we see that we don't quite fit within the experimental results. However, the moment we deploy the porous boundary condition, we see that the results lie very nicely within the experimental points. The same occurred with a different Reynolds number. Again, with the homogeneous boundary condition, we're not quite there, but with the porous, it lies there very nicely. So then, since we had the thorough numerical investigation, we could look at, okay, what was actually causing this destabilization in the blowing case and the stabilization in the other way around. The destabilization in the non-blowing case, but the stabilization in the blowing case. And so we looked at the two extreme cases basically, and we could identify 4 competing effects. So there is the fact that blowing increases the growth rate locally, so that advances transition. Then there is the fact that the porous surface decreases the growth rate locally, so that delays transition, so it goes against the previous. And then there is the fact that both blowing and the porous surface increase the range of unstable frequencies. So that means that so both of these actually advance transition, but coupled in including all these at the end, the outcome is different depending on the amount of mass that you're injecting. All right, so that was on the numerical experimental investigation. The second was, as I said, the investigation on the injection gas composition, and this was motivated by a series of experiments that were conducted by the NASA guys in the 70s, and where they basically wanted to look at how injecting gases with different compositions affected the transition front. Because, well, when we have an actual ablating surface, the pyrolysis and ablation gases have a ton of different species have different properties. So it's interesting to know how species with different properties, or more than different properties, with different weights affect the transition dynamics. So the most meaningful result that they obtained was that the injection of lighter species resulted in a sooner transition than when injecting heavier species. So again, we went ahead and said, okay, can we reproduce this numerically? So we chose a very similar geometry with very similar free stream conditions, and chose a test gas, which was just nitrogen and oxygen, so just air, plus an additional external non-reacting gas, which could be either helium, neon, argon, or CO2. which, as you can see, they have very different molar masses. So we have the entire range of lighter than air all the way up to heavier than air. And so what we saw is that just the blowing of these gases themselves actually had the opposite effect. So if we have a continuously blowing surface with these gases and we don't account for porosity, what we saw is that actually lighter gases were stabilizing, so delayed transition, whereas, or expected to delay transition, whereas heavier gases advanced it, so were destabilizing. So then we asked ourselves, okay, so there is definitely something in the experiments that we're not considering in our simulations. So we went through our entire list of hypotheses and started basically getting rid of them one by one to see at what point things changed. And what we managed to identify is that the trends that we were observing experimentally were due to a combination of, indeed, the gas composition that was different, but also combined with the surface porous characteristics and the fact that we were blowing in a discontinuous way. In particular, this discontinuous blowing combined with the gas composition originated a very small shocklet close to the injection region, which actually acted like a thermoacoustic impedance, which coupled with the porous admittance indeed appeared to be what was causing the experimentally observed destabilization due to lighter species. So to summarize our isolated blowing analysis, what we established is that the E to the N method can be applied to cases with surface blowing with the same N factor as non-blowing cases. We saw that the porous boundary condition can be used on transpiring surfaces, and it actually provides a modeling improvement. And we identified 4 competing effects, which was the destabilization due to the blowing, the stabilization due to the porous surface, and then the change in the range of unstable frequencies due to both the blowing and the porous surface. We were also capable of establishing why, so the reason for the advancement of transition when injecting gases lighter than air. And it was actually due to a combination of the porous wall admittance and the thermoacoustic impedance of the concentration shocklet. And in fact, we observed that the light gas injection, if in a continuous fashion, without accounting for porosity, actually had the opposite effect. So it was delaying transition. Okay, so that was on the analysis of blowing in isolation. So then we looked at chemistry effects. Actually, this is what kept me busy for the most time during these past years. Once again, we had 4 different lines of research, which again coincide with the 4 sections of chapter 10. The first of them was a study on the sensitivity of the results to high enthalpy modeling, which we published in Physics of Fluids last year. The second was an investigation on diffusion effects, which we presented at the SciTech conference 2 years ago. The third was a study on the adequacy of the various flow assumptions at different Mach numbers, which we presented together with Ludovico Zanos in the 2019 aviation conference. And finally, an investigation on ionization effects, which we presented at the ECANS Congress 2 years ago, and actually for which we got the prize to the best student paper. And actually, well, a spin-off of this investigation with a lot more depth and theoretical studies is currently under review at the Journal of Fluid Mechanics. Okay, so let's start with the sensitivity to high enthalpy. So I will focus only on the first and the fourth of these investigations because, well, I consider that they are the most interesting ones. So starting from the study of the sensitivity to high enthalpy modeling, the motivation here was that once we started looking at what had been done in the past with high enthalpy stability studies, we saw that authors had used a wide variety of different models for the thermal properties, transport, diffusion, chemistry, you name it. And very often they were reaching pretty different results. So it was very hard to know up to what point the discrepancy between the results was just purely due to the actual models that they were using, or if it was some numerical error, or if it was actually due to some physical phenomena that was going on there. So what we did was we went ahead and implemented all these models and effectively compared the results of one to the other, always taking as a reference the state of the art. And kind of the meta conclusion that we reached is that modeling is important. So modeling errors are important insofar as they affect the prediction of the boundary layer height. So for example, transport properties were seen to very strongly misrepresent the boundary layer height and therefore strongly affected the results. Actually, with this comparison, we were capable of explaining a discrepancy between two different research groups, which had remained unexplained for more than 20 years. So as I said, the impact of the transport model was pretty dramatic, and we actually saw that using the less accurate Blotner-Oyken-Wilk model could lead to an error of 38% in the expected transition onset location. So this is pretty huge. It's almost 50% of it's almost half of your vehicle, just purely due to the error in this transport modeling. However, what we surprisingly found is that the chemical reaction rate constants had almost no effect on the expected transition onset location, because what we saw is that at the streamwise position where perturbations would reach a sufficiently large amplitude so as to trigger transition, the flow was already in equilibrium or almost equilibrium. So the actual finite rate of these reactions didn't modify much the ultimate transition location. So that was rather surprising. Okay, so that was on the sensitivity to high entropy modeling. As I said, the next block I will talk about is the investigation on ionization effects. So for that, we looked at three trajectory points in an aggressive planetary return mission, and we chose a wide variety of flow assumptions in order to decouple the different physical phenomena that were going on. So what we did is we performed E to the n studies on each of these cases, and then by taking a single streamwise location and by comparing the results with the different flow assumptions, we could build these sort of instability budgets, let's say, associated to the different physical phenomena. So basically comparing a thermally perfect gas to a calorically perfect, we are capable of isolating the effect of internal energy excitation, or comparing a 5-species reaction gas to a non-reactive gas, we can isolate the effect of dissociation, and so on. So what we saw is that both internal energy excitation and dissociation are overall destabilizing, so they increase the maximum n factor, whereas ionization has the opposite effect. These results we obtained accounting for the finite rate of the chemical reactions, but if we actually assume the reactions to be in equilibrium, we were surprised to see that we were actually getting the opposite effect. So regarding ionization, so we were seeing that ionization appeared to be destabilizing. So we then looked at this a bit closer, and we realized that these equilibrium investigations also assume the perturbations to be in equilibrium, which is a rather questionable assumption, because it means that these perturbations actually have a very short time oscillation, let's say. So very often they don't have time to reach equilibrium within their oscillations. So if you actually relax this assumption and you allow the perturbations to move, let's say, freely without assuming equilibrium, what we get is the expected trend, so that, or at least a coherent trend with the finite rate simulations, and it's that ionization is in fact destabilizing. So we can say that this apparent result of ionization destabilization was actually an artifact of assuming equilibrium perturbations. Aside from that, we also used different flow assumptions on our perturbation terms, and that way we were capable of isolating what part of the destabilization was due to the base flow cooling and which one to the actual terms on the perturbations. And what we saw is that the base flow cooling is in all cases strongly destabilizing, whereas the perturbation diffusion fluxes, as well as the dissociation and ionization chemical source terms, were all stabilizing. So as I said, there's these once again competing effects. It just turns out that the base flow cooling is dominant, and therefore overall it is ultimately destabilizing. actually, the destabilization due to the base flow cooling can also be, well, is also associated to a stronger thermoacoustic impedance that is observed in the chemically reactive cases. So we have a stronger density gradient, and so basically this confines our second mode waves more, and so they become more unstable. With this analysis, we also looked at supersonic modes, which are commonly believed to be promoted by the chemically induced cooling in these situations. But what we actually saw is that accounting only for the cooling of the base flow actually had the opposite effect. It moved our instabilities away from the supersonic range, and it was actually the diffusion fluxes acting on the perturbations that were driving down the wave speed and making our second mode supersonic. So that was a quite surprising result. So to summarize our investigation on chemistry effects, we first looked at modeling errors. We saw that modeling errors affecting the boundary layer size were the ones that conditioned the second mode predictions the most. And we identified that using the Blotner-Eucken-Wilk transport model predicted a 38% sooner transition than the state-of-the-art models. However, chemical reaction rate constants were seen to have a pretty minor effect. We saw that internal energy mode excitation is overall destabilizing, whereas dissociation, and so is dissociation, while ionization is stabilizing. We identified that base flow cooling strengthens the thermoacoustic impedance and is strongly destabilizing. However, the perturbation diffusion and chemical source terms counteract this and are actually stabilizing. We also saw that supersonic modes in hot wall situations are promoted not by the base flow cooling, but by the effect of diffusion on the perturbations. Okay, so that was on the isolated effect of chemistry. The last part of our work was looking at both blowing and chemistry together when induced by an ablating graphite sample. So this is the work that we presented at the aviation conference last year. And again, an extended, more thorough investigation is currently under review at the Journal of Fluid Mechanics. So again, what we did is we took 4 points in a space return atmospheric mission, and again we got a bunch of different flow assumptions and boundary conditions in order to effectively decouple the different phenomena that were going on. So if we arrange our flow assumptions here on at the different columns, the boundary conditions at the different rows. For example, if we fix one flow assumption and look at the different blowing boundary conditions, we can, well, blowing and surface temperature boundary conditions, we can identify their isolated effect. Similarly, if we fix one same boundary condition and look at the different flow assumptions, we can identify the effect of internal energy mode excitation and air chemistry, both between say neutral air, air species and also carbon ablation subproducts. And of course, if we look at the, let's say, an 11 species mixture with carbon products and everything, and varying the surface boundary condition, we can isolate the effect of the surface chemistry. So this is what we did. Again, we performed a bunch of e to the n computations and then built these budgets by comparison of one or another flow assumption with each other, or some of the different boundary conditions. And so again, for the different flight envelope points that we were looking at. And what we saw is that, well, overall, internal energy mode excitation was destabilizing for all of them, and that then most of the phenomena associated to ablation, unsurprisingly, had a stronger effect for the stronger ablating cases. The only phenomenon that was actually stabilizing was the effect of the surface chemistry on the perturbation boundary conditions themselves. Yeah. So it kind of falls in line with the previous results that I was discussing. Okay, so to wrap it all up, we've developed simplified models for instability development in the presence of ablation, and we've implemented them into versatile tools to solve both the base flow and the stability problem. We've established that the e to the n method and the porous boundary condition can successfully be applied to blowing experiments. And we've identified the mechanisms involved in advancing transition when injecting gases lighter than air. We made a review of all the thermophysical models that were previously used by other authors studying stability, and we quantified their accuracy and the error that one could expect when using them. And finally, we used state-of-the-art models to investigate competing effects in very high entropy scenarios with dissociation, ionization, and ablation, decoupling them and identifying and quantifying their individual contributions. So looking forward, we believe that the effort should go towards incorporating also thermal non-equilibrium into these analyses. We should extend our investigations to more complex and realistic geometries and to more physically inclusive stability theories. And finally, we believe that the deployment of the high entropy compressible version of the Reynolds-Orr equations would allow for a more effective and insightful decomposition of the contribution of all these physical phenomena to the actual perturbations and their growth rates. So finally, I would just like to acknowledge all the people that worked into this, which were, well, the VTI Transition Modeling Group and the Texas A&M Computational Stability and Transition Lab. Without them, this thesis would be a shadow of what it is. And finally, the Belgian National Fund for Scientific Research, who funded all this through the FRIA Fellowship. So thank you, and with that, I will take any questions.
Thank you, Fernando. So I think we have now time for some questions. Let me first say that the jury members who are not present, so Dr. Radespiel and Professor Reed from Texas A&M, were very impressed by your work, and they applauded it very heavily. For instance, the detail and the scrutiny of your analysis, the effect of the transport models, for instance, on the results, the verification of the codes. It was extremely well documented and extremely well analyzed. For instance, also the work on the convergence of simulations was very convincing. So you did all these studies in extremely scrutinized detail. So then, of course, all the different phenomena you looked at. So these were the comments of the jury members who were absent. But let's now see for the other jury members if there are some additional questions. Maybe I start with Thierry Magin. Is it okay?
Sure. Yes. Yeah. So congratulations, Fernando, for your presentation. It was very clear and very didactic.
Thank you.
So I will have two questions. The first one is, could you give more details about the treatment of thermal non-equilibrium that you propose in the outlook? What do you have in mind? Is it boundary condition treatment we talked about, or what is it specifically?
Well, I guess the boundary layer, the boundary condition treatment follows like a, it's a requirement in order to do these sort of analyses, right? But it would not only be at the boundary, of course, it would be accounting for thermal non-equilibrium everywhere, basically. So as you well know, so having two temperatures, one for the transitional rotational modes, and then another one for vibrational, electronic, and electron energy. So the standard two-temperature treatment.
Mm-hmm. Because at the wall, usually it's assumed to have thermal equilibrium, right? So it's a strong assumption, but
right, yeah.
We don't know what's the consequence of this assumption.
Sure. That's yeah. That's okay. Definitely one line of work.
Mm-hmm. So then my second question is more related to the future work. So you have developed an impressive suite of tools that can be used now. There is lots, it's very rich in physics. You've performed already some sensitivity analysis, but I was wondering if you are planning in the future, or if you've seen people doing already a stochastic treatment, because you have uncertainties for all of these models. So how would you proceed? What would you suggest for the next generation, let's say?
So yeah, actually I didn't include it in the outlook, but that would be probably the most interesting thing we could do regarding the modeling uncertainty, because of course we've evaluated the accuracy of all these models based on the state of the art, But then the question is, how accurate is even this state of the art, right? So all these collision integrals often have a plus minus 10% if they're in their error bars. So if you then propagate all that, what will happen? I have no idea. But indeed, that would be one of the paths to go. I don't know of anyone that is doing it, to be honest. But sure, I would love to see that.
Yeah, and the chemistry, usually the uncertainties are even larger than in this case, especially for the ablation rates, etc. So
yeah, of course.
Would be interesting. Okay, so thank you very much. So that's all for me.
Okay, thank you, Thierry. Then I would propose that Alessandro Parente ask some questions if there are left. Thank you.
Yeah, first of all, thank you, Herman, for asking me. So first of all, I would like to congratulate also Fernando for the very nice and didactic presentation. I would actually go on with because we already discussed many aspects during this private defense. So going on the question that Thierry was asking. So you have a very complex multiphysics problem. So you probably expect that you have a very large number of uncertain parameters that would possibly affect your results. How do you see the burden or like the complexity of this problem ahead of providing, let's say, predictions with confidence? How do you see, in a way, approaches to determine which are the most important uncertain parameters in your problem? And do you see ways to actually move in that direction?
So you mean basically to giving a plus minus error bar on all of these investigations? Like how sure can we say?
So I mean, you will have to manage a large number of uncertain parameters. So you will have to, in a way, decide which are the most important ones, and also you will have to decide whether to propagate them intrusively or like non-intrusively in your simulations. So have you ever thought, I mean, do you have an idea of a strategy to move forward in that direction?
To be honest, I haven't looked much into like all these uncertainty quantification methods. Like, well, I've seen a few presentations at VKI, but it's still pretty foreign to me. So I'm not really familiar with what techniques they exactly use to propagate all these uncertainties. So I'm not sure I can give you a very good answer on that. Yeah.
But I mean, do you think it would be feasible to intrusively change your codes to actually include potential addition of, or you see it's very difficult, it's rather more realistic to manage, let's say, with a Monte Carlo-like of approach, these uncertainties?
So what do you mean by intrusively? So actually changing the expressions in order to
like
solve to not points but waves of points, or like
distribution inside your, like send distribution inside your codes?
I don't know. As I showed at the beginning, the code is pretty modular. So let's say the modeling part is pretty separate from the rest of it. So I don't know. I wouldn't, again, I wouldn't bet my salary on it. But I think if there is a code with, let's say, possibilities to do this, it would be this one, because it's as I said, it's very modular. So yeah.
Thank you.
Yeah.
Thank you. So yes, before giving the word to the supervisors, I would like to ask you also one question. So in fact, the question is about how could you control, in fact, the boundary layer or the transition, the transition. And in this respect, was it possible, or did you analyze the effect of temperature on the wall temperature separately from all the other effects, like blowing or chemistry, let's say the composition of the chemistry and so on? Did you also look at just a pure temperature effect or not?
Right. So I didn't do much work directly on the temperature effect, but this is pretty well established. So we know that basically wall cooling strongly destabilizes the second mode because it basically increases this. Well, it makes your boundary layer smaller, so your density gradient is a lot stronger. So basically, your instabilities are confined. Are more confined, so they become more unstable. So that's a pretty well-known phenomenon, that basically anything that cools down your wall is going to destabilize second mode, and whatever heats it up is going to stabilize it. And the opposite is true for first mode. I didn't speak about first mode instabilities here, but they actually have the opposite effect. They are.
And this effect, if you decouple, can you decouple it from, for instance, blowing? If you blow, you probably also cool the wall if you blow from inside, or how would you think about that?
So actually, I know that the DLR team, they were trying to have so just exclusively on the blowing here. So they were trying to blow at a certain, a very, very low mass flow rate, which was cooling the boundary layer, but it wasn't still destabilizing. So it was an idea they had there. They presented it at last UTAM, but it was still pretty preliminary. I don't know where they got. The wall warming, so the temperature one is a pretty common one. So for example, the Dr. Cool's team, they were trying to use it to actually to control, I don't know if it was first or second mode instabilities. Anyway, they were just doing a few simulations with adding a certain a range of patches on the surface, right, and then controlling the temperatures there and seeing how all these instabilities were modulated. So indeed, these are some let's say transition control, or instability growth control tools out there.
Okay, Thierry, did you want to comment, or did you? Oh, okay, no. So then the word is to the supervisors. Maybe first Fabio, please.
Okay. So yeah, thank you, Herman. Thank you, Fernando, for the presentation. It was very comprehensive, even though there are some time limits. So congratulations for that. I have a sort of question going back to where we started, like years ago, and so we verified. For instance, I start from the fact that in sometimes we have to go through very harsh simplification in our modeling, and for instance, one of these things is the shock boundary condition that I already implemented, and then we verify that, for instance, in the injection and the shocklet caused by the injection of lighter or heavier gas, considering or not the shock boundary condition has a strong impact on the stability, on this evaluated stability of the flow. It doesn't necessarily reflect what it is. So now that we have all this packaged together, or blowing ablation chemistry and wall reaction, I would ask, what would be your take on the possibility of making this kind of analysis with a more comprehensive model, like for instance porous surfaces, so where you consider everything at once, and basically you bypass entirely the problem of a boundary at the wall, and you estimate everything at once, possibly in like true way.
Right. Yeah. Actually, well, as you well know, that was the original goal of the project, right? Like we didn't quite get there, but the idea was to solve the entire domain with these with Argo, which solves also inside the porous surface and so on. Yeah, as I said, we didn't get there. I think even the base load tools were not quite there yet. But I think the derivation and implementation tool is at a very healthy stage, so it's that we could, like, adding new equations or boundary conditions is relatively easy at this point. So you basically just have to write down the equation in invariant form, which, well, that's another bag of worms. But once you have it in invariant form, if you express it correctly, then the rest is pretty much plug and play. So I think we're at a very good stage to take on that.
Would you expect a substantial difference?
That is an excellent question. I have no idea. Because it's true that the porous condition is it imposes an admittance on this wave propagation. So I don't know if we would have to have an incredibly detailed level of simulation within the porous surface to actually get that. Right, because this admittance is somewhat of a macroscopic quantity. Yeah, but even also I'm just thinking out loud here. But also the unified approach is also averaged. So yeah, who knows?
Yeah. Yeah, for the future.
That would be, yeah.
Okay, so
Very nice
thank you. Thank you, Fabio. So before giving the word to the public for some questions, please, Gérard, go ahead as the second supervisor.
I will be short. I first want also to congratulate Fernando for a remarkable piece of work. It's really impressive to see the amount of first of all, the amount of phenomena that he looked into, and of course the required modeling effort that goes together with it.
Thank you.
As I was, well, in fact, hearing your presentation today, which is a very clear presentation, by the way, and reading the thesis, I came up with the following paradoxical, what I say, idea that eventually you showed quite clearly that cooling down the wall is destabilizing.
Mm-hmm.
Okay. And
not even the wall, but the boundary layer, wherever it is.
Boundary layer.
In the center of, not necessarily the wall.
Cooling the boundary layer is destabilizing. Okay.
Right.
But of course, this cooling the boundary layer is done by, for example, the ablation phenomena, the blowing of the thing, by the existence of the thermal protection system itself. So the purpose of the thermal protection system itself is to cool down the boundary layer, and on the other hand, this cooling down destabilizes the flow. So
well, I would say the purpose of the thermal protection system is to cool down the inside, right? Like,
yes, right.
Boundary layer doesn't really care.
In order to cool down the inside, you have to cool down the boundary layer.
Right.
Okay. So eventually, does that not mean that the proper design is the design of a system that cools down just enough so that the thing don't grill inside, but not more, so that it doesn't destabilize the flow?
I guess so. I guess, but then the question is, how much is enough, right? Like, the devil is always in the details.
Yes.
But yeah, indeed, it seems like it.
Okay. So that clearly means that oversizing, in fact, to have a strong, too large a cooling effect is definitely not beneficial.
Sure, but then again, if you undersize, then it's the end. So
yes, that's correct. So it's a subtle equilibrium to find there. Yeah.
Where there is a lot to lose, I would say. So.
Yeah, sure. Okay. That's it for me. I would just want to draw your attention, Herman, to the number of questions that are asked in the side window, and in particular, there is a remark by Helen, who was attending, in fact, the presentation as a watcher, and who also congratulates you very much for a clear presentation and an impressive work.
So I don't see this, Gérard, this side window.
I mean, you have on the control bar. So you have camera,
seeing them actually. If you want, I can read them out. And
share, and then you have a little window with two lines that is for the conversation. So you can display the conversation. And then of course there are a couple of questions from the audience, which I can read for you if you like.
Yes, or Fernando. Or
as you prefer. I'm seeing them myself also, so I could. So yeah, I can start with the question by Andrew. He says, with regard to what you've learned about the effects of various transport, thermal, and chemical models on the linear growth of instabilities, would you say that including more nonlinear effects in the stability growth or analysis of the thermal and chemical effects on receptivity is more important moving forward? I'm not sure what he means by more important. Like, more important than what? More important than like if the inclusion of the nonlinear effects is more important than that of the chemistry, or Not sure.
Vibrational non-equilibrium, possibly. I don't know.
I don't know if Andrew can remake that question. Can't see it. Anyway, meanwhile, maybe I can address another one. So Ms. Lyon here is asking, hello, excuse me, it is a very basic question. I am not familiar with the field. I cannot comprehend whether these results are purely theoretical for the moment, or if they can be put into practice right now. So, well, some part of the results were actually compared to experiments. They were all ground test experiments, but still, it's not just some theoretical fantasy world that we're building here. Indeed, always comparison against experiments, especially in high entropy situations, it's a big challenge because, well, finding a facility which can actually reproduce the conditions that you have in flight is really, really hard, which means that either you should basically have some sort of flight experiment which has, well, it's just incredibly expensive and complicated. So I guess to answer your question, yes, they are. I mean, most of them are theoretical at this point. But yeah, that's what we have. Like, there aren't that many experimental results out there. I hope that answers the question. I don't see any further asked questions.
So you saw the Andrew Riha, you saw this?
Right. But I'm not sure what he means by more important, like more important than what? Would you say that including more non-linear effects in this?
Yeah. But this is the question you just looked after, or yes?
I answered to the last one, so the one by Ms. Lyon.
Lyon, okay.
So I would say that like, given that now we have all these effects, that we find out that the nonlinearities are even more important than we used to think. This is, I think, what so it's like in the next future, should we focus even more on nonlinearities, or just the two things are not necessarily, let's say, bound together? This is what I got from the question.
So I don't think it's possible to conclude on the effect of nonlinearities from my work directly. Like, I didn't look at nonlinear effects at any moment, so I wouldn't dare to say anything about that. I know Ludo has started to look at it, but again, with nonlinear effects, there's a bunch of other problems. Like, you have to take into account the mean flow distortion, so you have to recompute all your properties on the fly, and well, there's a ton of other hurdles associated there. So I would say that we're not ready yet to say this or that phenomenon strongly affects nonlinearities, because, well, we haven't looked at it yet. So yeah.
There is a comment by Andrew. There is a sequel.
There's the first?
Yes.
Oh, right, I'm seeing it now. I mean, as the most important next step in accurate transition prediction, would you say that including more complicated growth dynamics with simplistic receptivity, or more complicated receptivity with simplistic growth dynamics? Ah, okay, I see. So if we should put the modeling effort into the thermophysics or into the receptivity, let's say. Well, I think receptivity is definitely the elephant in the room. Like, we're performing these modal growths based on a initial amplitude, but nobody's really sure what this initial amplitude is. So if I had to put my money somewhere, I would definitely put it on receptivity. And actually, I think the U.S. Air Force agrees with that, because they're shoving money on it a lot. So.
Okay. Then we have a question from Ethan. Can you elaborate on the physical reasoning that the isolated phenomenon of ionization on non-equilibrium perturbations is stabilizing for your problem? Or will the proper answer require the Reynolds or equations? So can you elaborate on the physical reasoning behind the fact that the isolated phenomenon of ionization on non-equilibrium perturbations is stabilizing?
So yeah, that was one of the most surprising results, actually, to see that ionization actually stabilized the flow. we were actually so when we entered that investigation, what we were expecting is, okay, so with ionization, we have a drop in viscosity, right? Because ions have a much lower viscosity. And since second mode waves are generally stabilized by viscosity, we would expect that ionization that decreases viscosity would actually destabilize them. But actually, it was the opposite. Like we got a stabilization, and so for sure with the Reynolds-Orr equations, we would get a better grasp of what's going on. But already with what we have, what we saw is that the inclusion of ionization basically changes these competing effects that we were seeing. So if you remember, there was a stabilization due to internal energy, so baseflow cooling basically, and then our diffusion fluxes and chemical source terms counteracted it. And what happens when you include ionization is that the relative weights of these guys changes. But yeah, that doesn't really tell us much on like a base physical phenomenon going on there, like a physical reason. But that's always a challenge to find.
Okay, so I think this concludes the session with the questions. I see no further questions, and time is of course running. So then the jury will retreat for the final evaluation, and so the session will stay on, if I understand. So we will not end the live event, but the jury will open now a new session. I think, Gérard, do you know a bit more about it?
I think you're muted, Gérard.
Yeah, I'm muted. I guess we have to open the other link that Lucina was sent.
Okay.
Yeah, you have another invitation for another.
So it's another channel. Okay.
Right.
So sorry, should we hang up on this and just Fernando stay online?
You have to type leave. You have to go on leave.
No, leave or live. Leave, live or leave?
Leave. You have to leave this event.
Yeah, okay.
And where is it?
Leave, yes, I see it. Okay, so we leave this event. I hope we can come back.
Yeah, you can. I tried that before.
Okay.
Okay, so I'm going to mute. Meanwhile, the jury meeting goes on, and I'll be back.
Sweet.
So Fernando, we finished now the deliberation with the jury members, and I will give the word to the secretary of the jury, Alessandro Parente, to read the decision of the jury. Please.
Thank you, Herman. So I will have to read this in French. So I will start reading now. La séance du 30 avril 2020, doctorat en sciences de l'ingénieur et technologie. La séance est ouverte à 16h30 sous la présidence de M. Herman Lekonik. Sont présents les membres du jury constitués par l'École Polytechnique de Bruxelles. Alessandro Parente, secrétaire. Gérard Degrez, promoteur. Fabio Pinna, situant Karman de dynamique des fluides. Thierry Majan, toujours VKI. Ellen Reed, de Texas A&M University, USA. Rolf Radespiel, Technische Universität Braunschweig, Germany. Donc, Monsieur Fernando Miró Miró, titulaire d'un diplôme d'ingénieur aéronautico délivré par l'Université Polytechnique de Madrid, ainsi que d'un certificat de formation à la recherche en sciences de l'ingénieur et technologie délivré par l'Université Libre de Bruxelles, défend publiquement le travail ci-dessous accepté par le jury. Numerical investigation of hypersonic boundary layer stability and transition in the presence of ablation phenomena. Après délibération à huis clos ou à, disons, Teams clos, le jury décide de conférer à M. Fernando Miró Miró le titre de docteur en sciences de l'ingénieur et technologie. En conséquence, M. Fernando Miró Miró est proclamé docteur en sciences de l'ingénieur et technologie. La lecture du présent procès-verbal est faite en séance publique et la séance est levée à 18h09.
Okay, thank you.
Yes. Félicitations.
Félicitations, Fernando.
Merci.
Thank you. Not only for a thesis, but I would say for an extraordinary good thesis. Thank you, Fernando.
Isn't it an exceptional thesis presented in exceptional conditions.
Definitely exceptional conditions. Yeah.
So it should go viral. No?
Well,
Okay, so thanks everybody, also the listeners from outside, so the public. And with this, I think we will close the session, except if anybody else has still something to say.
I wanted to ask Fernando whether he has organized an online drink.
An online drink. I think it'll be presential with the people at home that I can have it with, but no online drink.
Yeah, okay. Because it has become fashionable these days to have online, right?
Okay.
Yeah, it was already enough of a hustle to set up the online.
Yeah, okay.
I just want to add a few words, as it's very unusual. So first, I want to congratulate. It would be nicer personally. I hope we can do it in the following days. And it was a pleasure. So it's like 6 years almost of work together. So you expanded a lot what I started, which is very nice to see. And I think we really collaborate nicely. So I learned a lot. I hope you learn as well. And hope that we can we can go on collaboration unnecessary on transition or something else. And thank you very much. And you really deserve this reaching this goal and this achievement. Thank you very much.
Yeah, thank you. The feeling is mutual. Like it was great to work with you, and yeah, I've learned a gigantic amount. So thank you.
Thank you. With these final remarks, I think we can close the session. Have a good evening and a good first May weekend later on. Thank you, everybody, and bye-bye.
Goodbye.
Okay.
Have a nice evening. Bye-bye.
Bye.
have a nice evening. Bye.